my pleasure to introduce Erin May. So Erin did her undergraduate at Michigan State University in astrophysics and math, double major, then moved on to the University of Michigan, where she worked with Emily Rauscher, and did her PhD there, and has since moved on to very briefly Space Telescope Science Institute in Baltimore, and then to the Johns Hopkins University's Applied Physics Lab, where she currently is and has been there for a few years as a postdoc. So Erin works on all sorts of aspects of characterizing exoplanet atmospheres, including ground-based observations, space-based observations, and also running global climate models or general circulation models of these planets. So she has written very many first author publications on all of these topics, including, planets, like hot Jupiters, but going down to smaller planets. And is involved in all sorts of larger collaborations as well, getting lots of awesome and exciting data. So yeah, I'm really excited to hear about what you're going to talk about, Erin. Take it away.
Thank you. Yeah, so as Nick said, I'm currently a postdoc at Johns Hopkins Applied Physics Lab. A lot of people aren't familiar with the Applied Physics Lab. We're actually a university-associated research center of Johns Hopkins, so we're technically a separate institution, but also the same. We're 30 minutes down the road from the main campus, and we do a lot of mission development at APL. But APL is also really known for their planetary science, and they're starting to get involved in exoplanet research, which is where I came in and got my job at the lab. So I'm going to talk today about one aspect of my research and what I've been focusing on the most for the past few years. And this is Spitzer and the population trends we can derive from phase curve observations with Spitzer. So I'm going to start with some introductory level material for any of you that are new to the field of exoplanet observations. And if you are an expert, because I know there are several of you in the room, this is a great chance for you to take a bathroom break or get more tea or coffee, even though I know there was technically a tea session just before this. But before I start going into this introductory material, I want to highlight some of the amazing science in general that Spitzer has done for exoplanets, because I'm always interested to find out that not everybody knows that Spitzer devoted a lot of its time to studying exoplanets, not just with phase curves. So one of the most amazing things that Spitzer did for exoplanet science is it's responsible for the first spectra of extrasolar planets. So HD 209-458b and HD 189-733b used to be like the two exoplanets to study, mostly because they were the only two that we could study with transiting observations. And Spitzer got the first look at molecular features in their atmospheres and really paved the way for spectroscopic observations of exoplanet atmospheres. Spitzer also was responsible for the first map of an exoplanet. So this is again HD 189-733b, because at the time it was all we could observe. That was also a really exciting time because we got the first look at how the heat was, where the heat was located in the planet's atmosphere. And then moving away from hot Jupiters, Spitzer was also monumental in the confirmation of 5 of the TRAPPIST-1 system planets. So this is a system of 7 planets, where a lot of them are around the size of Earth. So Spitzer really was instrumental in paving the way towards us being able to start to characterize terrestrial systems, because this is going to be one of the most exciting targets for JWST observations of terrestrial planets, starting in a few months now. But this talk is obviously about phase curves, and Spitzer spent a lot of time on phase curves. So specifically during the warm part of the mission, after it ran out of cryocooler, Spitzer observed nearly 60 phase curves of about 31 exoplanets, and this totals up to around 3,000 hours of observation time. This corresponds to about 10% of the original primary JWST mission time, when it was expected to only last for 5.5 years. But even still, even now that JWST is going to last for 20 years, this still remains a large amount of time that Spitzer dedicated to exoplanet phase curves that we're just not going to be able to replicate with JWST observations. So this means that Spitzer is going to remain this treasure trove of exoplanet data, and we're not going to have to worry about JWST coming in and telling us we're wrong about all of it, maybe only some of it. With that, I want to talk about what a phase curve is and why we even care about taking these observations since they take so much time. So there are a few different ways that we can observe transiting exoplanets, and I'm specifically going to focus on transiting observations here. There are some great ways to characterize planets that don't transit. I'm not saying that I don't care about them, but I'm not talking about them here. But transiting observations are really the key to characterizing the atmospheres of exoplanets. So on the bottom here, I have a little schematic of what a phase curve looks like. And this would be in relative flux versus time space on the y and x axes. On the top is a schematic of the planet's orbit. So the first thing that we can look at when a planet is in a transiting orientation, so it's oriented in the right angle, is the secondary eclipse of the system. So this occurs when the planet crosses behind the star, and the star is occulting the day side flux from the planet. So we're assuming that all of these planets are tidally locked when they're close enough to their stars. So they have a permanent day side and a permanent night side. When the planet is passing behind its star, its day side or hottest hemisphere is oriented towards us. And the amount of flux that's missing during this time is equivalent to the day side emission from the planet at the wavelengths that you're looking at. And directly in the middle of the eclipse, we get a measurement of just the star flux. And this is important because it gives us a baseline level of the amount of flux coming just from the star, so we can compare that to flux at other times and determine how much of it is being contributed from the planet itself. And there's a car alarm going off outside. Sorry if you can hear that. But the next thing I want to highlight in here is the transit of the system. So this occurs when the planet crosses in front of the star. And at this point in time, we measure the planet to star radius ratio. So the amount of light blocked during the transit, so this bigger dip here, is proportional to the radius of the planet divided by the radius of the star. So if you had a bigger planet or a smaller star, you would get a larger signal. And not only that, these planets, for the most part, seem to have atmospheres. And these atmospheres are not completely opaque. So some light can pass through the planet's atmosphere and interact with whatever gases or molecules or clouds are present in the planet's atmosphere and actually change that transit depth slightly to account for extra absorption from the planet's atmosphere. And that's what we call a transmission spectrum. Now, between secondary eclipse and transit is where the phase curve observations happen. And because these planets are assumed to be tidally locked, as it transitions from secondary eclipse to transit, more of the night side is coming into view and less of the day side of the planet is visible. So the amount of flux from the system decreases from the time of secondary eclipse until the time of transit. And we can measure that difference between the peak of the phase curve that occurs around the time of secondary eclipse and the minimum of the phase curve that occurs around the time of transit. And that tells us something about the difference in temperature or emission between the day and night side of the planet. This is useful because these night sides never directly receive flux from the planet's star. So it tells us about how efficient the planet is at moving heat away from the day side and onto the night side due to the winds in the planet's atmosphere. And also tied into the winds is the fact that these planets have really strong day-night forcing due to this temperature difference. So your hottest hemisphere is not always directly aligned with the actual day side hemisphere of the planet because these winds can blow the heat away from what we call the substellar point, the point that the star is directly above, and move it eastward due to the strong winds. And when this happens, we actually detect that peak of the phase curve before secondary eclipse, and we can measure how far early that occurs, and that tells us something about the strength of winds and the type of circulation in the planet's atmospheres. Now, one thing that's going to be really great about JWST is we can take these observations spectroscopically and look at more wavelengths, broader wavelengths of light, which gives us broader insight into different pressure levels in the planet's atmospheres. But until we get JWST in the sky, we've been doing a lot of Spitzer observations with a lot of phase curve observations with Spitzer because planet emission peaks in the infrared wavelengths. So on the right, I'm showing a 1500 Kelvin black body curve. And I've highlighted the 4 Spitzer IRAC channels, which is the instrument on Spitzer that was used for this. When Spitzer ran out of cryocooler, we were no longer able to observe with channel 3 and channel 4, and we began to focus just on channel 1 and channel 2 observations, which correspond to bands centered at 3.6 and 4.5 micron observations. So this really gives us an insight into the emission from the planet. On the left, I'm highlighting the entire population of known transiting planets. We got equilibrium temperature on the y-axis and orbital period on the x-axis. And the size of each circle corresponds to the size of the planet. Now you might notice that of all of our phase curve targets, these targets in stars, they're really clustered at short orbital periods. And there's a few reasons for this. One is that the longer the orbital period, obviously we need to spend more time observing them. And it's hard to convince TACs to let you stare at the same object for 20 days. And not only that, the larger the orbital period is, the cooler the planet is likely to be. And then that leads to less signals from the planet's atmospheres. So we're primarily looking at what we call these hot Jupiters, Jupiter-sized planets that are really close to their stars, because we expect them to be tidally locked at that point, where we have that strong day-night contrast to measure that signal, and have the strong winds to measure the phase offsets in the planet's atmospheres. Now, this sounds great. It sounds like Spitzer is the perfect telescope to study planetary emission because it's observing at infrared wavelengths. And it was really our only instrument to do this until JBOOST comes online in the coming months. But like most telescopes, Spitzer was not designed with exoplanets in mind. So the raw observations from Spitzer are often a complete mess. And I say that with utmost love for the Spitzer telescope itself. But what I'm showing you here are two sample phase curves from two random planets. So orbital phase is on the x-axis, and the eclipses would occur at 0.5 and 1.5 in orbital phase, and the transit occurs at 1 or 0, and then just raw flux currents on the y-axis. And what we saw a few slides ago was that we would expect there to be a clean dip occurring at the transit and a clean dip occurring at the eclipse and some smooth variation between the two. But that's not the case that we see with most observations. Even on the one on the right, where we see maybe a clean transit here and some smooth variation, this is a huge amount of variation, much more than we would expect from the planet itself, and we can't clearly see any eclipses. So the reason is that Spitzer has really strong systematics, and these are primarily dominated by what we call intrapixel sensitivity variations. So if you're an observational astronomer, you might be familiar with the idea of flat fielding, where you have to remove the effect of each individual pixel having different sensitivities when you're taking observations. But the intrapixel effect actually is a result of there being different sensitivities within a single pixel. So the Spitzer PSF is really undersampled. So as a result, if the center of your star falls in a different spot within a single pixel, the amount of flux you measure can vary by several percent. So as an example of mapping out the sensitivity of a single pixel on Spitzer from a paper by Ingalls et al. In 2012. And you can see as you move from the center of the pixel out to the corners of the pixel, there's a 6% change in the amount of flux that's measured from the star. And this is absolutely huge when we're talking about exoplanet level observations that are 1% or lower. So not only does the amount of flux measured change just based off of where you are on the pixel, but the shape of your PSF actually also changes as you move around on the pixel. So as you drift to the edges of the pixel, your PSF stretches into more of an oval instead of a circle. And this is a big problem when we're doing circular photometry, because you end up missing some of your light when you're counting up the amount of photons you've received from the star. This is a smaller effect than the intrapixel sensitivity, but it's large enough that it actually does matter for some of our phase curve observations, since we're trying to measure these really tiny signals of a planet orbiting a star. So in order to go from that really bad, crappy data, we need to be able to remove this intrapixel and PSF effect. So we do all of this within some iterative process, typically at MCMC. And the first thing we do is we select an astrophysical phase curve model that's representative of what we would expect. And these are typically made up of sinusoids or spherical harmonics to describe how we would expect the planet to vary between the eclipse and the transit. If we're also fitting for this PRF effect, the next step is to fit this polynomial form to these trends in the Gaussian width, which is what I mean by GW here. So these are some examples of as the Gaussian width shifts in both the Y and X direction, the amount of flux as measured, and we can fit that and remove that from our data. We then take our astrophysical phase curve model. Sometimes we also have some trend in time, a linear trend or an exponential ramp, and this fit to the Gaussian widths. And we look at the difference between that and what we've measured on the detector. And we take that, and because we know exactly where the center of each of these observations fell on the pixel through our centroiding, we spatially bin them into what we call a pixel map to represent what we would have expected the sensitivity on the underlying detector to have been. This gets interpolated back onto the exact locations of our data, which is a method called BLIS mapping, or bilinearly interpolated sensitivity mapping, to represent how the flux varied as the star moved around on the detector itself. And all of these together allow us to explain how the flux has jumped up and down throughout the course of the observation in combination with the planetary astrophysical effects as well. So once we get to something like this, we can divide out our systematic models, and we're left just with the astrophysical variation of the planet and star system itself. So there's a lot going on here, but the end result is we're generally able to remove these effects, even though they're quite a bit larger than the planetary signals that we're looking for. However, it's not as clear-cut as it seems, because we're talking about two effects, the PRF effect and the intrapixel effect, that vary as you move around within a single pixel. So we looked more closely at this for the WASP-43 data set, and what I'm showing you here is the Gaussian width in the Y dimension compared to the centroid on the bottom, zoomed in on some subset of exposures, and these are relative effects. What you can see is some strong correlation between the shape of the Gaussian, so it's stretching out more as the centroid drifts. And this is exactly what we expect. If the centroid drifts towards the edge of the pixel, we expect the Gaussian width to shift and change. So we performed a continuous wave transform analysis on this, and what we found was that they're heavily correlated on the order of a few exposures. So this is our absolute continuous wave transforms on the top for the centroids and on the bottom for the widths of our Gaussians that get fit for both channels and both dimensions. And they both peak at around 20 exposures or 40 seconds for this data set, with a 3 sigma limit around a few exposures. So as a result, if we were to temporally bin the data, we end up smoothing over all of the features that make these unique and able to be fit independently. And the reason this is important to think about is because these data sets are typically very large, and many methods to remove the systematics are computationally expensive with these large data sets. So typically, it's easier just to temporally bin our data. So we thought we'd look at that and see what happens when we actually do bin the data. Do our results vary? So this is again the WASP-43 data set, and I'm not showing the data points here, only our best fit functions. And we tried 3 different functions for our phase curve. So we have a sinusoid example for the phase curve function, spherical harmonics, and Lambertian, which is what you would expect for reflectivity, not emission. And we tried fitting our BLIS mapping with not including this PRF detrending against those Gaussian widths, and also including that PRF detrending. And we progressively binned the data. So yellow is no binning, up to purple is binning by 32 exposures. And on the top row, you can barely see any more than a single line, which tells us that there's no significant change depending on how much we bin the data. We're getting the same result, which is good. But many groups have found you end up with better results if you do use this PRF detrending. Now on the bottom, what we found was as you bin the data, when you use the BLIS mapping and the PRF detrending to remove additional systematics, you end up having results that drift away from the no binning results until a bin size of 32, which is the largest we tried. Now these drifts are larger than the uncertainties in our fits, which means the best fit result is not necessarily your best fit at a given bin size. It's dependent on the bin size that you picked. And this is bad because we're already dealing with systematics that are huge compared to our signal size. And if we're also having problems where the way in which we reduce our data changes our results, it's hard to know what the correct answer is. So naturally, if you have two results or two models that are degenerate with each other, this bliss mapping and PRF, you want to find a way to hold one side of it constant. So traditionally, when we do this bliss mapping, it's essentially a self-calibration on the data. Well, what are the residuals between our data and our model, and how can the underlying map explain that? But we know there has to be some actual real underlying function of the sensitivity on the detector. So we took a similar result, or similar path to that the Ingalls et al. Map I showed on a previous slide, where we generated an up-to-date intrapixel sensitivity map based off of calibration data for Spitzer IRAC. So it's expanded on the map from the Ingalls et al. Work, and it also uses the exact same data reduction techniques as our Spitzer pipeline for phase curves. So the centroiding is performed in the same way, and the aperture photometry is performed in the same way. And I'm specifically showing you the 4.5 micron map we generated here. This black spot corresponds to what many people refer as the sweet spot on the detector, where it performs the best on these long period observations. And many of this is coming from calibration data for the telescope. And we've recently added on a large number of centroids from some phase curve observations of GJ1214b, which is a very small planet that is expected to have phase variance that's within the uncertainties of Spitzer observations. So if we cut out the transits and eclipses, we're left with essentially an observation of a quiet star that we can add on. Now, this is all for 4.5 micron, which is great, but 4.5 micron observations are not typically the problematic ones with Spitzer. 3.6 microns is a little bit more of a challenge. So we really wanted to be able to find a way to improve some of the analysis methods for 3.6 microns. However, we end up finding that 3.6 microns is a time variable sensitivity. So what I'm showing here, we split our calibration data into 3 discrete points in time and compared these points in time to each other. So these are difference maps between different groups of time for 4.5 micron calibration data, compared now to the same method done for 3.6 micron calibration data. These are on the same color bar. And what we found was significant time and spatial variability in the channel 1 sensitivity that made it pretty much impossible to derive a fixed sensitivity map at 3.6 microns as the data stands. So one of the things that we're actively working on is understanding the source of this variability. And we have ways to check to make sure it's not the underlying calibrator star itself, and also using additional calibration data to try and understand how this sensitivity is changing if it's the detector itself, because we'd really like to be able to perform a similar method on the 3.6 micron data. So this first takeaway here is that we don't think Spitzer data should be temporally binned. So it's computationally expensive to not bin it for many analysis methods, but it's beneficial not to make sure we're not smoothing over these small parameters that allow us to confidently remove the systematics from the data. As a part of this, we did develop this new detrending tool for 4.5 micron Spitzer data, and we're starting to apply this to the entire set of Spitzer phase curves, so we can perform a uniform analysis. So for an example, we applied it to WASP-43b, which is a prime example of how even really well-behaved Spitzer data, where well-behaved depends, I guess, on who you talk to, the results really can vary based off of how the data is analyzed. So these are 4 different analyses of the WASP-43 phase curve. And the yellow one on the bottom is our new analysis with this fixed sensitivity map. Some things to note are that our new night size temperature is much more in line with some of the newer analyses, but our phase offset is not. And one of the things that we found with our fixed sensitivity map is these previous analyses didn't find any statistical significance for asymmetry in the phase curve because they're self-calibrating. And there was when you add the additional parameters of the asymmetry, it's not worth it in the model fit. But when we perform this fixed sensitivity map removal, that all happens before we go into the phase curve fitting. And so these underlying asymmetric trends can't be modeled away by the Bliss mapping. They're part of the underlying astrophysical signal at that point. And that drives us towards having a larger phase offset, actually. But one of the most exciting things is that our new night side flux is more aligned with 3D circulation models than the original reduction by Stevenson et al. In 2017. And I'm showing now on the right, on the top is hotspot offsets, and we're going to ignore this because the models don't match a single hotspot observation for a variety of reasons. But these are from a paper by Mike Roman in 2021. On the bottom, this is the amplitude of the phase curve on the y-axis as a function of irradiation temperature, which is just a square root of 2 difference from equilibrium temperature. The old WAS43b reduction is shown in gray, where my cursor is, and our new one is shown in blue, and it's much more in line with expected models at that gravity that are cloudy. So this is promising that our new technique is performing better in matching circulation models. And it's a major reason, this whole idea of, depending on how you analyze the data, you get different results. It's a major reason why some groups are moving to these multiple independent reductions of a data set so that your result is cognizant of all of the possible systematic models that can explain the data set. But my takeaway number 2 is that the scatter that we currently see in these trends that I showed on the previous slide might not actually be astrophysical, because we have been able to change the results with our new reduction method. So we think a uniform analysis can mitigate some of this, because we'll be removing the same systematics from every data set, instead of looking at a bunch of data sets that have all been analyzed in a different way by a different person. So to start for this uniform reanalysis, we're starting to go through the phase curves that haven't been published so far. So the first one I want to highlight is WAS76b. This is an inflated ultra-hot Jupiter. And there's been a lot of ground-based observations of the planet recently, detecting signs of iron condensation on the night side. So this is a beautiful artist rendition of Singing in the Iron Rain on WAS76b, as the iron is condensing on the night side of the planet and forming this cliff of clouds. If you're interested in reading more about these high-resolution ground-based observations, I listed some of the papers there, and there's been a lot more since I made these slides as well. So the reason we wanted to look at this planet is that theory suggests that you need a hot internal adiabat, so a hot internal temperature on the planet, to inflate it to its large radius. And this would most strongly affect the night side of the planet, because there's no irradiation from the star there. It's only going to be the internal temperature heating up the planet on that side. And phase curves allow us to test this, because it's a unique way to probe the night side emission of the planet. There's really no other way to do that for a transiting planet. So before I get into the science results here, I want to highlight that these are results from a co-first author paper. And if you have questions about how to cite this properly in your work, please send me an email and I'll send you 2 lines of LaTeX to include in your overlay file or LaTeX file, whatever you use, so it shows up properly into the text and both authors get the credit for the work. So with that said, I'm not going to spend a lot of time talking about the specifics of the data reduction of each of these phase curves, because I told you how we did it already. But we did have 2 phase curves at 3.6 microns and 1 at 4.5 microns. I'm showing the 3.6 microns on the left and the 4.5 microns on the right. There were just 2 at 3.6 because of some problems with the observing setup at the telescope. It's not because we thought that that channel was any more interesting. And at 4.5 microns, we ended up, we used our fixed sensitivity map, but WAS76 has a nearby companion that falls 0.3 pixels, Spitzer pixels away. So we actually applied 2 fixed sensitivity maps to account for the fact that the star and its companion were going to be on different regions of that single pixel. And as they moved around together, the amount of the flux response for each of those components would change independently. And that worked really well, and we were left with, after removing both the components, the stellar components, we were left with a very clean phase curve. We also compared those phase curves to 3D models in this work. So these were using the MIT GCM, and we compared a cold interior model and a hot interior model, because we're trying to test this idea that you need this hot internal adiabat to inflate the planet to its large radius. In addition to looking at different interiors, we looked at different drag timescales. So the left here is as cold interior models, and the right here is hot interior, and we're looking at maps of the brightness temperature from the model. And as we move from top to bottom, we're increasing the drag strength, which corresponds to a shorter timescale for drag in the atmosphere. And some of the things I want to highlight here are typically expected things from this type of set of models. But that overall, we had stronger winds in the cold interior models, because you end up with a stronger day-night forcing. You don't have as much additional heat on the night side, so you get a stronger temperature differential to force the winds in the planet's atmosphere. And we also found that these strong drag cases, where drag is less than 10 to the minus 5, so these bottom two panels, were primarily characterized by just overall day-to-night flow, which includes winds flowing over the poles, westward, eastward, not this traditional equatorial jet that we get in some of the weaker drag cases at the top. You see the heat is just really pushed away from the substellar point along the equator. So we took these and post-processed them into observable phase curves in the two Spitzer bands. And what we found was that unexpectedly, the cold interior models matched our observations better. So on the left is our 3.6 micron phase curves. On the right is our 4.5 micron phase curves. The top is the hot interior and the bottom is the cold interior, with each different line is a different drag timescale in the atmosphere. And in general, these cold interior cases did a much better job at reproducing the observed night side emission from the planet. In addition, we needed to invoke the strong drag cases to best match the phase curves, primarily the phase offset of the observed phase curves. And this is interesting because many of the ground-based observations required a weak drag in order to explain these strong limb differences between the morning and evening terminators and get that iron condensation happening. It's possible that we're just probing different regions of the atmosphere. And so future work needs to look at that more. But I will say that no model can actually explain all of the observed phase curve parameters. So these are some of the observed phase curve parameters on the y-axis with drag timescale on the x-axis, and the horizontal bars correspond to our observations, with the width of them being our uncertainties, and the lines correspond to the model predictions. So some takeaways are that our cold interior models really only moderately agree with our 3.6 micron data, but it's not uncommon that 3D models don't agree with Spitzer. So it's not necessarily a cause for concern, though we do have reasons to not trust the 3.6 micron data very much. And some caveats are that our models are cloud-free. It's probably not a big issue for ultra-hots. The night sides are probably a little bit too hot to have strong cloud coverage anyways, but it still might be important, and we should look at including those. They are double gray models, which means you only have an optical and an infrared band, and a constant absorption occurring in both bands, so they're not really representative of the actual optical properties of the planet's atmosphere. And then we do also apply a uniform drag timescale everywhere in the atmosphere. But we know things like magnetic drag will actually be spatially dependent for these planets, especially at these ultra hot temperatures like WASP 76b. But our lack of hotspot observation, which was in agreement with effectively a 0-degree offset, does agree with previous observations of ultra hots like WASP 103 and WASP 18. And recent work does suggest that these ultra hot planets might have strong enough magnetic drag to explain this lack of hotspot observation. And I want to highlight a recent paper by Haley Beltz et al. That looked at applying magnetic drag in the atmospheres using a 3D model, where the magnetic drag was spatially dependent based off of the local ionization of the atmosphere. And these are some temperature maps from her models, increasing the amount of magnetic field as you move from the left to the right. And as we move from top to bottom, we're just moving deeper in the planet's atmosphere. But what I want to highlight, if you look at the top row, when there's no magnetic drag, these lines represent the winds. You get this typical equatorial jet forming, but as you increase the amount of drag, you get this day-night winds where the winds even move over the poles away from the day side, similarly to what we found in our high drag cases, with the difference being that this drag is pretty much only present on the day side in these models because you need that hot temperature to ionize the atmosphere. So even if we do include this more physically realistic drag, we actually get better agreement with our observations of no hotspot offset. And then one last thing I want to point out about this data is that if our 3.6 micron data does hold true, and we do have reasons to maybe distrust it, then WASP-76b is one of the first planets that we can clearly say that we have detected a day-side inversion and no night-side inversion. So day-side inversions are not uncommon. We do a lot of emission observations with just an eclipse, but the fact that we've also confirmed that there's no night-side emission is fairly unique because getting these phase curve observations of ultra-hots are not common. So my third takeaway is that we need better models. This is no hate to the modelers because I am one as well. But because phase curves are uniquely probing the entire atmosphere, we need to make sure our physics in the models includes everything that could potentially affect everything in the atmosphere. And many models do lack the things like radiatively active clouds, stratospheric inversions, hydrogen dissociation, magnetic drag that can be important physics at different temperature regimes. So with all of that said, what I'm currently working on is analyzing the remaining unpublished Spitzer phase curves before we get into the total reanalyzing of all of them. So this is back to that plot I showed back at the beginning of equilibrium temperature versus orbital period, highlighting all of the phase curves that Spitzer observed during the warm mission. And these yellow ones are the unpublished ones as of when I made these slides a few months ago. I have an upcoming submitted work that looks at 5 planets with a total of 8 phase curves, all of them around an equilibrium temperature of 1300 Kelvin, with a goal of looking at population trends within a single small population at the same temperature to look to see if some of these trends hold within small subsets of the population. So our data in this ranges from well-behaved to what was Spitzer even doing. Again, I'm not going to spend a whole lot of time talking about the data analysis process here because I went through the steps at the beginning, but I just wanted to highlight what the telescope was doing for each of them so you get an idea for maybe how trustworthy some of the observations are. But this is looking at the raw flux on the bottom of each panel and the centroids on the top for both X and Y. And you can see some of them like WASP-34b, which was a very long observation, was jumping around a lot. And each of these line breaks corresponds to when the telescope had reacquired the target. And there's also weird things like the telescope had to stop in the middle of this WASP-34 observation to downlink data. So we ended up with a gap in our observations. But we did apply our fixed sensitivity map when it was applicable. So we could do a uniform analysis as uniform as allowed by the data, of course. The caveats being that we can't currently do that at 3.6 microns because we don't have a method in place for fixed intrapixel sensitivity removal. Qatar 2 does not overlap with our current map, and we are working on expanding it more so that hopefully we can overlap eventually and actually use this method. WASP-52 had some weird things going on with the shape of our PRF. So it wasn't an oval when we expected it to be, and it wasn't a circle when we expected it to be. So we had to do some additional reduction steps. WASP-34b was my what is Spitzer even doing? It was kind of jumping around, doing all kinds of things. And it was also the last phase curve Spitzer observed. So there was also some weirdness in that data set. But Qatar 1 and WASP-140 were great data sets to analyze, and they worked really well with our methods. Qatar 1b was already previously analyzed by Dylan Keating in his 2020 paper, and our results do agree with that. We did just want to reanalyze it here because it's the same temperature as all of the other planets. So as I said, our analysis is as uniform as allowed by the data, and I'm not going to talk too much about each of these individual things, but I do want to point out that WASP 140b has a very slight eccentricity and a very weird phase curve. So we think it might actually just not be tidally circularized yet. So it only recently arrived at its orbit, and it's very possible that what we're seeing is just not a hot Jupiter that's tidally locked with one permanent day side and one permanent night side. And then WASP 34b, in addition to being a very long data set, is actually a grazing event. So the planet only skims across the star during its transit and eclipse. But the point of all of this is to start to look for population trends and uniform data sets. And that's why I'm giving this talk. So to start talking about some of the trends, we do find evidence for a trend of increasing eastward offset with orbital period. So as the planet gets further from its star, we find that it has effectively stronger winds blowing around the planet. And the top, I'm highlighting that trend just for our population of 1300 Kelvin planets, ignoring WASP 140 because there's some potential that it's not tidally locked. And on the bottom, it's that same trend of offset versus orbital period for the full population. And this is dynamically interesting because theory doesn't predict a dependence on rotation rate, which is effectively a proxy for orbital period for tidally locked planets. Theory does predict that the hotspot is driven by the ratio between the radiative and advective timescales in the atmosphere, but we know that rotation doesn't affect the radiative timescale. So this existence of this trend suggests that the rotation rate has implications on the wind speed in the atmospheres of these hot Jupiters. And this is observationally testable with high resolution observations from the ground. Sorry. And this is very interesting that we find this trend is not just statistically significant in the full population, but also in our 1300 Kelvin sample. And we're really excited to continue reanalyzing some of the other data sets to see if this trend continues to hold, because it's really being driven by some of these just a couple longer period data sets. We also look at what's called the apparent redistribution as a function of equilibrium temperature. So this is the ratio between the day side and equilibrium temperature in the planet's atmosphere. And I've marked a few lines on here corresponding to an atmosphere with effectively no heat redistribution in the atmosphere, day side only redistribution, and then full redistribution around the planet. And these trend lines here are from models by Parmentier in 2021. The thin lines correspond to 4.5 micron emission predictions, because this is, I'm looking at only trends at 4.5 microns here. And the thicker lines correspond to bolometric predictions. So what's interesting here is that our 1300 Kelvin sample, so we have Qatar 1, WASP 52, Qatar 2, WASP 34, and WASP 140 span a really wide range here, suggesting that this is actually going to depend on a lot more than just equilibrium temperature, like models predict. And it's also interesting because these planets are below the threshold where MHD effects are expected to kick in and affect the day-night heat transport. So for example, WASP 52 and Qatar 1b have hotter than expected day sides. And if these planets were in general hotter, we might be able to explain that away with MHD effects, but they're actually too cold for that to matter. So we can't just say, oh, unmodeled physics is the reason why these don't match model predictions currently. And then we also look at trends of offset and amplitude as a function of equilibrium temperature. These are similar plots to what I showed before. The grayed out sample is the rest of the population, and the solid circles are the planets in our current survey. The purple and blue lines are from the models from Mike Roman in 2021. He has two different gravities and both clear and cloudy models. And then the orange lines are from Parmentier in 2021, where NS stands for night side, and those are different size cloud particles. In general, there's not great agreement between offset and models, and that's probably due to these cloud effects that need to be better understood. But we do find good agreement between our new results and the phase curve amplitude predictions from both the models from Roman et al. And Parmentier et al. We do think there's kind of maybe in general a systematic offset between the offset and the models, and do find that better agreement. But we're going to be working on some adding some additional physics into our models to hopefully explain that in the future. And we do interestingly find that 2 of our planets are showing evidence of being clear atmospheres, and 2 of them are showing evidence of being cloudy atmospheres. And it's really encouraging that they do line up with model predictions. One last thing I want to point out is that there's maybe some offset versus gravity trends. So we see these low gravity planets have larger offsets, and these higher gravity planets in our current 1300 Kelvin sample have low offsets. So if we look at offset versus gravity space, and these are color coded versus equilibrium temperature, we add some very rough trend lines by the eye. We're seeing potentially maybe a flattening off of the relationship between offset and gravity with increasing equilibrium temperature. And this might be due, for example, to these ultra hot planets having effectively no hotspot offset, regardless of gravity, because of those magnetic effects on the day side, really destroying your equatorial jets. So my takeaway number 4 is kind of the same as takeaway number 2, is that the scatter and the current trends might not be astrophysical, and we're working on cleaning that up by performing a uniform analysis. And we are adding additional physics into our 3 models to hopefully better explain the trends that we do see. So I like to end all of my talks with what I call a talk and a tweet. So if you were tuned out until now, this is all you need to remember, that this current scatter is not entirely astrophysical, and we're adding in additional physics and performing a uniform analysis to mitigate some of this. So stay tuned for work from our team over the next few years as we work through these problems. With that, I'm happy to take questions.
All right, I see lots of clapping hands, including mine. So thank you for that talk. Yeah, there's time for questions from the audience. You can either type it in the chat or you can raise your hand. To get us started, I have a question, which is how easily, like the sort of master map that you made for Spitzer IRAC, how easily does that carry over to spectroscopic observations? And is this something that you could envision applying to some of the spectroscopic data we're going to get with either James Webb, or even more promisingly with something like Ariel, where we're going to have uniform observations for like 1,000 targets?
Yeah, so what we need to make something like that is a lot of calibration observations. So you need a telescope that will devote a lot of calibration time to just staring at a star that we know is constant. I actually saw something recently that one of the stars they were planning to do that with for JWST turned out to be a variable star. So not only do we need to stare at a star for a long amount of time, we need to know it's a constant star. And then it will be entirely feasible to generate a map like that for any other instrument, if these intrapixel sensitivity variations actually are a problem for it. We do need to make a different map for each aperture used. So if you change your aperture size, that affects like the strength of the PRF effect, for example, or how much background noise you get into it. So we had to make a map for every aperture size we might potentially ever use for these Spitzer observations, and it's time consuming. There's 4.5 million data points that were used to make our map. And there's a lot of iterative processes to make sure that the absolute scaling of each chunk of calibration observations is correct. So it can be done, you just need to devote the time to it. And I do think, it might not be as important for spectroscopic observations because you can kind of use a nearby wavelength channel to make sure that your data makes sense. Like there shouldn't be strong changes in your phase curve for nearby wavelengths. And with the photometric stuff, you don't have that simultaneous observation at a nearby wavelength to convince yourself that the systematics are taken care of. That was a long-winded answer to say yes and no.
So, okay, wait, so just a quick follow-up on that. The calibration data that you're talking about, like how long is that compared to like a typical exoplanet phase curve?
It was taken over the span of, I'm trying to remember, a very long time. It's not just staring at the same star for a couple days. There's like periods in time where they would stare at these calibration stars for a little bit, and then they'd come back a couple days later and stare at it again for a little bit, and then come back another time and stare at it again for a little bit. And then there were like 3 discrete points in time where they dedicated a lot of time to staring at it. So it's separated by a long amount of time, which gives us confidence that we weren't seeing any temporal variations in the sensitivity at 4.5 microns. And that's also why we were able to find that sensitivity variation at 3.6 microns, because it did change over time.
Got it. Cool. Okay, thanks. All right, other questions?
Hi, Erin.
Lisa?
I have a question. So I was curious about the analysis that you did with binning data and that influencing your night side temperature measurement. So it seems like the more you bin the data, the warmer the night side retrieved were. So I was wondering whether there was a reason why that happened sort of like systematically.
Yeah, so I mean, this is just one data set that we looked at, WASP-43b. I'm not entirely sure, why they all seem to trend warmer, other than the fact, I would have to pull up, what the centroids were doing at that point in the observation. Maybe they were, moving in a very particular way where it became really easy to confuse astrophysical with systematic signal at the same time. If the centroids were moving really quickly, it's really easy to confuse astrophysical and systematic. So it's possibly what was happening there. But if I did the same analysis for a different data set, it's very possible we would see, not very possible, we would definitely see a different change in results in a different way as we binned it, because each data set is unique.
Right. Well, that was my I guess my follow-up question was that did anyone do this analysis for other data set than the WASP-43b data set? Or
we haven't. So what we do find is that, so I don't bin the data ever, essentially. The Bliss mapping isn't as computationally expensive as some of the other ones, like PLD, pixel level decorrelation. But what we did find, and I don't show this panel here, is when you use the fixed sensitivity map, even with the PRF detrending, there's no variations with binning. So there's another 2 panels at the bottom of this in this paper that show the same exact test done when we use our fixed map instead of the free map, and this problem goes away.
All right, thank you.
All right, are there any other questions or comments? You can write in the chat, raise your hand.
If there is no one, I have another question.
All right, Lisa, you're up.
So in your uniform analysis paper, one of them had a slight eccentricity, the WASP 140b.
Yes.
Just out of curiosity, I think you said that you think that the planet recently like settled in that orbit, as in it's migrating. So basically, what does it have any companion? Is that how you ruled out, or basically how you assume or presume that maybe the planet is migrating?
Yeah, so that's all from the discovery paper. It's a fairly young system, and the orbital circulation timescale is almost, I think it's on the order of, better than on the order of the same as the age of the system. So, and because it has that slight eccentricity, there is a suggestion that it might have just recently arrived, and that's why it's not perfectly circular yet. And then we looked at the phase curve and saw that it looks weird. One of the possible explanations for the fact that it has this westward offset is that it's slower than synchronously rotating, and that would be explained by the fact that it's only now just getting into its orbit from a longer period orbit, essentially.
Cool, thank you.
If I had more time, I would run some great models for this planet and try and see if we can explain that large phase offset with slower than synchronous rotation. But I do not have time for that. So
yeah, I'm just thinking that maybe it'd be fun to compare that with like planets with higher eccentricity, like Exo 3b.
Yeah, another thing that I didn't mention is that the peak of this phase curve, while there is a huge uncertainty on where the peak occurs, it's fairly flat. It is roughly aligned with the periastron passage as well.
Well, at the very least, we could throw some undergrads at this and have them run an energy balance model and see whether, whether prograde or retrograde rotation was more consistent with.
Yeah. I'll also add this was this data set has 3 non-overlapping AORs. So for people who aren't familiar with that, there are, we want all of our centroids to overlap so that we can, so when you take these observations, the telescope has to stop and repoint every now and then, and we want it to repoint at the same exact point on the detector. And if it doesn't, it becomes hard to detrend them because these independent chunks of centroids can kind of move all around. And this one does have 3 independent chunks of centroids. So you can see in the bottom corner. It was essentially verging on impossible to reduce without using our fixed sensitivity map. So for all of these, we reduced them both with and without that to make sure the results didn't change significantly. And this one, it could not converge on a good answer unless we used that to constrain the fact that they had these 3 non-overlapping centroid regions. So it's entirely possible that there's just other weirdness in the data set as well. But the fact that it is not eccentric and it's a young system and where did my mouse go does make sense given the phase curve.
Cool. Okay. I think we've made it to the bottom of the hour, I guess, the end of the full hour. So thanks again, Erin, for a really interesting talk. And thanks everyone for tuning in. And I think that's it. So Carolina, I assume you'll like turn off the video and the recording and stuff at some point.